Let's take a look at exponential functions. This is a graph I like to show in my classes. This is the national debt. And you see it starts over here, Truman, and then it's going Eisenhower, Kennedy, Johnson, so forth. Hits Carter, goes up a little bit. Hits Reagan, goes up quite a bit. Bush Sr. goes up quite a bit. Hits Clinton, and Clinton about levels this off. If he had had another 4 years, you would have saw this actually go down. Unreal what Clinton did. If you look at the numbers, they're just so close to being leveled off. And then Bush Jr. took over, and it goes up like that. And then Obama takes over, and it goes like that. Now, a lot of people don't understand the national debt. They don't understand exponential growth. This is the nature of an exponential growth. It goes slow, goes slow, goes slow, and then all of a sudden it flies out of sight. Now, this has nothing to do with the wars. Well, I mean, a little bit, but war itself doesn't cause it to go straight up like this. If you look over here, we just got done blowing up Japan. So we're rebuilding Japan, rebuilding Germany, Korean War, Vietnam War. And you see it's not even really much significant difference. Obama. He comes into power, and people sitting there, they blame us on the Obamacare, the health care plan. Well, these Einsteins that were saying that, when they're saying that, it hasn't even taken effect. So it's just like, God, what are you talking about? Try to have some sense to you when you discuss this. Again, this has nothing to do with Obamacare. This has nothing to do with the wars. This is the nature of an exponential graph. What Bush Jr. did wrong in terms of just the national debt part, there's a lot of other pieces to how the country's doing, but what he did wrong here is he just undid what Clinton had put in place. If he had kept what Clinton had put in place finance-wise, you would have saw this go down, and he would have been the hero of the country in terms of getting us back on track with our finances. Now, when you look at this and you see this, it seems kind of staggering with it going up like that. You have to do something dramatic to get it to change from exponential growth, and that's what Clinton did. He increased taxes, cut spending, military, increased taxes not only for the middle class, for the rich people too. Now, taking that all into account, we had good jobs under Clinton, and the rich people even made money. So it isn't like that's going to destroy your country by having that. If Clinton hadn't done his little thing here, this would be a perfect exponential graph. So if nothing else, probably the most important thing you can get out of this is to understand that people looking at this national debt here has nothing to do with with Obama spending a lot of money, with Bush Jr. spending a lot of money. They anticipate now who we owe a lot of this money to is China. They anticipate by 2025, I think it was, that just the interest we're paying on our loans to China will be able to fund China's entire military. I think what I just said there, that's pretty wild. But again, when you get this exponential growth going, that's what happens. Now, at first, during the Reagan years, this wasn't borrowing money from China. That would have been unheard of to borrow money from the communists. He actually raided Social Security. And that caused all of Social Security's problems. Now, during this time, I had to take my dad to every political meeting there was. My dad was upset about it because he knew what they were doing. They were destroying Social Security, which is kind of bad for future generations. The idea of Social Security is kind of the same plan that Boeing had. My dad was retired from Boeing, and they had this chunk of money here, and all the current employees would pay into this. And only the interest would go out to the retirees. So only the interest would go to the retirees. So what you'd see is this money would keep getting bigger and bigger, and you'd have more and more interest. So it could cover more and more retirees. It could even cover part of their medical. My dad got really good medical through the retiree plan they had. This is the way Social Security is set up. All the people are paying in Social Security, and down the road, not at first, but down the road, Only the interest was to go out to pay the retirees. And this big chunk of money would keep growing and growing. You would see this exponential growth like this. And fantastic plan. Beautiful plan. The problem is when you start raiding money, you start taking money out of this and putting IOUs in it. Well, IOUs don't accrue interest. And that's what Reagan did. He raided Social Security. He saw this huge chunk of money sitting there that he could use to help get the country back on track. Now, he's not the only president that did that, but he's the one that really hit it heavy. Now, Bush Sr. Took over, and he kind of kept on the same practices, and Clinton and so forth. Now, I don't know where the money actually ran out here, but at some point we started borrowing from other countries, China real heavily. And then, that gets even worse. As you're paying them interest, as it gets bigger, this is what happens. Now, exponential growth is very big in business, so you'll see this a lot there. It's also pretty important in the medical field. You got infections. Well, it starts off slow. They're multiplying, and then all of a sudden, it grows exponentially, and you have your infection taking over and killing the person. So you have to study it there also. Now, I haven't updated this for a while, by the way. I'm not sure where my numbers even stopped. A couple years ago was the last time I updated it. So there's a lot you can study on this graph and so forth. But it's an interesting one. I like it because it shows exponential growth. Let me check to make sure I've actually got these saved. I'm re-recording. I had them in WebEx video, and I'm recording them in YouTube. Yeah, it looks like I got them. Yeah. Okay. So let's start taking a look at the problems in this section. This is kind of a calculator-based section. So our first one, we got 7 to the 3.1 power. And it says to approximate each number using the calculator, round your answer to 3 decimal places. So where's my calculator? There it is. So I'm going to do 7 caret and then 3.1. And then push enter. And our answer to this one will be 416.681. And that's our answer. Our second problem. We got 9 to the square root of 3. So we'll come over to calculator. We'll put in 9 caret, and I need the square root, so I'll do second x squared, and then 3, and I'll put a closing parentheses. I don't have to put a closing parentheses, and then enter. And we get 44.957. Our third problem, we got e to the negative 2.5 power. Now, e on your calculator, you access by doing second, then ln. That's the natural log button. So second ln. Excuse me. So I'll come over here. I'll do second ln. Now it puts the e, puts a caret, and puts the beginning parentheses. And then we got negative 2.5. And then I'll press enter. And take it to 3 decimal places, and we get 0.082. And that's our answer. Now, next one wants us to graph this. Now, if we were doing this by hand, we'd just plot points. So you'd build a T-chart and plot your points. We're going to show it on the calculator. T-chart to me is kind of boring. So we got 4 to the x power. Now, exponential function, what makes something an exponential function is you got a variable in the exponent. So let's go graph this. We'll press y equals, press clear, and I'll put in 4 caret and then x. and then graph. Now if your graph doesn't look like this, press zoom. So press zoom and you choose number 6 for Z standard. Now this looks like it just stops. It doesn't. It keeps going forever this way. So it's growing slow, growing slow, growing slow, growing slow, growing slow, boom, flies out of sight. That's just the nature of exponential graph. So that'd be our answer. I'll just kind of sketch it here. Like that. Let's take a look at our next example. We got f of x is equal to 1/4 to the x power. So I'm going to press my y equals, press clear, do a beginning parentheses, 1 divided by 4, closing parentheses, caret x, and then graph. Now this looks like it just stops. I never just stop. It keeps going forever this way. It just got so close to the x-axis it appears 1 with it. So it's going slow, growing slow, boom, flies out of sight overnight. Again, that's just the nature of exponential growth. You can fault Bush Jr. for many things, but national debt going up like that isn't because he's like spent a lot of money. I mean, that might be a little bit of it, but that's just the way exponential growth goes. What he did wrong, he just undid Clinton's work. Now let's look at this one. It says graph of an exponential function is given. Select the function for each graph from the following options. If we look at our basic graph, which is g of x is equal to 5 to the x. If I were to plug 0 in there, I'd have 5 to the 0, which is 1. So I know it passes through 1. And I know the nature of exponential graphs, so I know it looks something like that. Okay. Now these ones with a negative in front of them. Remember, a negative out in front of it flips it across the x-axis, reflects it across the x-axis. Well, this doesn't look like it's flipped upside down, so I could cross those off. Now the plus 1 here, that means it shifts it up 1. Well, if this is a 1 on the y-axis, up 1 would be a 2 on the y-axis. And this doesn't look like it's a 2, so that isn't one of your answers. We said this isn't the one, so it must be by default f of x. So f of x is our answer. If you think of what the minus 1 does inside with the x, if the number's inside with the x, it's left to right, opposite what you think. So the negative 1 would make you think left 1, so it's really right 1. And this does look like a shifted right 1 compared to this graph. Let's look at our next problem. Got g of x is equal to 4 to the x minus 1 plus 3. Now to graph this. Well, first, describe the transformation. Sorry. Plus 3 at the end means it goes up 3. Now minus 1 inside with the x, this means it goes right 1. So this one's up 3, right 1. Now to plug this in your calculator, unless you have one of the newer calculators, anytime you have more than a single variable or a single number in your exponent, you need to put parentheses around it. So I need to put parentheses around the x minus 1. So let me go graph this. I'll press y equals, clear, and I'll do 4 caret, and I'll put a beginning parentheses, x minus 1, closing parentheses on the exponent, and then plus 3. Now the difference on the newer calculators is when you do a 4 and then a caret, it throws you up in exponent mode. So all you have to do is put in x minus 1 and then press your right arrow key to get out of exponent mode, and then put your plus 3. Then I'll do a graph. And this is our answer. And notice it's growing slow, boom, overnight, flies out of sight. You'll get bored with these graphs because they're all the same. But bored is probably good. It will help you in the future not to sit there and blame somebody for for exponential growth when they have not. That's just the nature of it. Okay, let's look at this one. G of x is equal to e to the x minus 2. Now, to describe the transformation, the minus 2 up here means we're going to go right 2. It's opposite what you think. The negative 2 would make you think left 2, so it's really right 2. So let's graph this. Press my y equals, press clear. Then I'll do second ln for the e. And it puts the e, puts a caret, puts a beginning parentheses. And then we just need to put the x minus 2. And graph. And again, it looks like it just stops. It doesn't. It keeps going forever this way. So our answer would look like that right there. Let's look at our next example. G of x is equal to negative e to the x plus 4 minus 1. Now, to describe the transformation, this minus 1 at the end is down 1. This plus 4 right here is left 4. And this flips across the x-axis. You could also say reflects across the x-axis. Well, let's graph this now. So clear that out. Okay, y equals, clear, put in my negative. Then I want e, so I do second ln. I'm going to do my exponent now, which is x plus 4. Now, I'm on the older TI-84, so I'd put a closing parentheses. But for those on a newer one, you just have to press your right arrow key to get out of exponent mode. And then minus 1. And graph. Now, it's flipped upside down, but it goes slow, then boom, flies out of sight. It's flying out of sight down on this particular problem. But that would be our answer. Something like that. And that'd be your answer. Now, these next problems involve interest problems. So let's talk about interest. We have one formula that says continuous. They'll say it's compounded continuously. And then you'll have another formula that doesn't say continuous. So that's how you can tell the two formulas apart. Where it says continuous, that's our PERT formula. A is equal to P times E to the RT power. Where it doesn't say continuous is A equals P times 1 plus R over N to the NT power. Now, A is our ending amount. P is our principal, or our beginning amount. R is our rate, and it needs to be in decimals. Decimal form, that is. So if it's 3%, we'd use 0.03. Move it to your decimal 2 places to the left. T would be time, and it's in years. Now, N is the number of times compounded per year. Compounded is a fancy way to say it's calculated, and then you take the interest and you dump it right back into the account. So it compounds upon itself, grows. Now, if it says the word annual, your N is going to equal to 1. And if it says semi-annual, N is 2. If it says quarterly, N is 4. If it says monthly, N is 12. If it says weekly, N is 52. If it says daily, we ignore leap year, and N is 365. And occasionally they'll have hourly. Hourly is 365 times 24. Whatever that would give you. So looking at this, blah, 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 compounded semi-annually. That one doesn't say continuous, so you use the formula on the right. B, blah, 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 compounded quarterly. Doesn't say continuous, formula on the right. Compounded monthly, formula on the right. Last one, blah, 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 compounded continuously. Says continuous, so you use the PERT formula. So that's how you decide which formula to use. So let's look at A. So 10A. It says find the cumulative value of investment of 5,000. So they're telling us 5,000 is our principal for 20 years. So T is 20 at an interest rate of 3.1%. So R is going to be 0.031. We change it to decimal form. And then A says compounded semi-annually. Compounded semi-annually means N is equal to 2. So we've got A is equal to P times 1 plus R over N to the NT power. So plug in our values. Put 5,000 in for P. 1 plus R. R is 0.031. Divide by N, which is 2, raised to the NT power. So we'll have 2 times 20. Now you're better off to do a little bit of math in your head before you plug in your calculator. So everything is going to carry down. But 2 times 20 is 40. And now we'll put that in. I'll do a second mode X out of graph mode. And I'll do 5,000. Beginning parentheses 1 plus 0.031 divided by 2. Closing parentheses caret 40. Enter. And we get 9250.54. My wife and me had a bad fight one night about interest. Weird thing for a couple to fight, I know about, but we did. My wife came home from the financial planner. She'd started investing our money, and she was all excited. And she came home and she said, well, we're going to be investing $1,000 over this coming year, and at the end of the year, we're going to have $2,000. Well, I'm not a very nice guy. I'm kind of a jerk at times, and I know that. And sometimes the garbage just flows out of my mouth, and I can't stop myself. And I said, well, we need to get a different financial planner. And she said, well, what do you mean? And I said, well, he's dealing drugs. And, I'm not very nice about this and everything. And she got all defensive and everything. It wasn't a very good night. It was all my fault. I was right, of course. I teach it, so I knew. She went back and found out that no, she wasn't going to double her money in a year's time. But again, I was totally in the wrong because I could have said it very lovingly and nicely, and I didn't. Look at this. We're putting 5,000 in at 3.1%, which isn't too bad, for 20 years, and we still haven't doubled our money. So I knew there was no way we're going to double our money in a year's time because we're not like risk takers. We're going very low risk anyway. Let's look at B. Compounded quarterly. Quarterly. Well, that means N is 4. And we'll have the same values as this. So we're going to use A is equal to P times 1 plus R over N to the NT power. P is 5,000. 1 plus R, which is still 0.031. Divide by 4, raised to the NT power. So we got 4 times 20. Now you can put this in as you see it, but if you do, you have to make sure you put parentheses around the exponent. Because if you have more than a single number or a single variable in your exponent, you have to put parentheses around it. So I got 5,000, beginning parentheses, 1 plus 0.031, divided by 4, closing parentheses, caret And I find it just as easy to multiply these in my head and put those parentheses around it, so I'll just put in 80. And enter. And that'd be your answer. So 9272.45. Well, let's take a look at C. It says compounded monthly, so n is equal to 12. So same formula, p times 1 plus r over n to the nt power. P is still 5,000. 1 plus r, which is 0.031, divided by n, which is 12, raised to the nt power. So we'll have 12 times 20, which is 240, I believe. So let's come over here. Got 5,000, beginning parentheses, 1 plus 0.031 divided by 12. Closing parentheses, caret 240. Enter. And we got A is equal to 9287.21. Now D. It says compounded continuously. It says continuous, doesn't it? Which means when you want to use our PERT formula. So we've got A is equal to P times E to the RT power. Well, P is 5,000. E is just a number. It's like 2.7 and a bunch of decimal places. R is 0.031, I think. Yeah. Times T. Well, we're still doing it for how many years? 20. Now you have to be really careful when you plug this in your calculator. Let me show how to do it. So you put in 5,000, then you do your second ln to get the E. It puts a caret, puts a beginning parentheses. You're going to put in 0.031 times 20. Do not put any extra parentheses in. Type it in exactly as you see there. What people will try to do, let me write this answer down first. 9294.64. What people will try to do on this, most common mistake, is they'll do 5,000, second ln, 0.031, close parentheses, beginning parentheses, 20. And that kind of makes sense when you think about it. But then when you do it, you get 103,000. You get a number way bigger than you should be. And then you're having a fight with your significant other that night and regretting it years later. So again, you don't use any extra parentheses when you put this in. In one of my college algebra classes, I said, well, let's take into account. We're going to put $100 in the account, and our R is going to be the 0.031. And we're going to leave it there for 700 years compounded continuously. So we use our PERT formula. So we got 100 e to the 0.031 times 700 years. So we're going to have 100. Do second ln for the e, caret and beginning parentheses. 0.031 times 700. Then we get 2.66 E11. What that E11 means is this is 2.66 times 10 to the 11th power, which means you move your decimal place 11 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's see, that's a million, that's billion. So you'd have $266 billion in the account after 700 years' time. What would be cool about this is if you can open up a bank account, put $100 in it. Yeah, anybody can spare $100. Put $100 in it, and then just pass that bank account from generation to generation. 10, 15 generations down the line, whatever that would be in 700 years' time. All of a sudden, they're as rich as the Koch brothers, the KOCH. That'd be so cool. But again, there's things that stop this. Banks don't want you to do that. You have to have activity on an account. If there's no activity on an account, then they'll close it. And of course, the government, they'll charge taxes on this. So, but again, you can see what exponential growth does. It takes something that's nothing and takes to 700 years later, comes up with this big amount. Now again, the exponential growth question is, when does it do that ramp up? Where does it fly out of sight? Let's look at our last problem. It says, suppose you have 50,000 to invest. So P is 50,000. Which investment yields a greater return over 7 years? So they're telling us T is 7. Okay, 5.12% compounded quarterly. So R is equal to 0.0512. Compounded quarterly, that means N is equal to 4. It doesn't say the word continuous anywhere, does it? So we're going to use this formula. By the way, it's also, you wouldn't be able to find that kind of interest anymore. 3.1%. Okay, or 5.3%. So this will be 0.053. It says compounded semi-annually, so N is 2. Doesn't say the word continuous on this one either, so we're going to plug it into this same formula. A is equal to P times 1 plus R over N to the NT power. Well, we'll put 50,000 in for P. 1 plus 0.0512 over N, which is 4, raised to the NT power. And I'm going to go ahead and multiply these together. 4 times 7 is 28. Now over here, this will be 50,000, 1 plus 0.053 divided by N, which is 2, raised to the NT power. So we got 2 times 7, which gives us 14. Well, let's plug these in our calculator. So we've got 50,000, beginning parentheses, 1 plus 0.0512 divided by 4, closing parentheses, caret 28, enter. And this one would have 71,389.35. Let's do the other one. So we'd have 50,000 beginning parentheses 1 plus 0.053 divided by 2, closing parentheses, caret 14. Enter. And we get 72,109.98. So the one that gives us larger is this one right here. So this one would be give us a greater return. And we're done with that section, which is good because I need to go to class. So let me save this. Stop the recorder.